The next two sections are about optimization, which is a application of all of this work we've been doing, finding maximum and minimum values on a function. Now we're just looking at those questions in an applied context. So the process you're going to go through as you're doing optimization is first you're going to model the restriction. And the restriction is what's keeping you from covering the earth with your item. It's what's keeping you from, if you're trying to maximize something, it's what's keeping you from making it minuscule, from making it, yeah, cover the earth. If you're trying to minimize something, it's what's keeping it from being just teeny tiny. Then you're going to write the optimization equation. When I write the optimization equation, I write it as f of x. Because I want to remind myself that that's the equation I'll do calculus on. That's the one that I'm going to have to find the maximum and minimum value for. So that's the one I'll take first derivative of and find the critical points. I'll go through this process with a bunch of examples. So here's the first example. You're building a fence around a yard. You have 500 feet of fencing. One side of your yard will be up against a building, so it doesn't need a fence. What dimensions give you the largest area for 500 feet of fencing? Your first job is to figure out what is keeping you from just filling up the whole world with this fence. And what's keeping you from doing that is that you have 500 feet of fencing. So your restriction is that this fencing amount, x, y, and another x, can't be any more than 500 feet. That's the maximum amount of fencing you can use. I'm going to simplify that a little bit as y plus 2x equals 500. And we're going to solve our restriction equation. Usually I solve it for y. It doesn't always work out that way, but this one I'm going to solve for y. So I have y equals 500 minus 2x. Now I'm looking at what am I trying to optimize. This is a completely separate equation from our restriction, so we shouldn't be thinking anymore about that restriction. We should start with what dimensions give you the largest area. So that's what we're trying to optimize, which is the area. So the area we're going to write as an f of x equation. It's a rectangle, so the area would be x times y. Now it should bother you a little bit that we have an f of x equation with an x and a y in it. The way we're going to get rid of that y is by using the restriction, so that our f of x equation doesn't need to have an x and a y in it. It can just be x times 500 minus 2x. That's what we're trying to optimize. So that's what equation we're going to use for calculus. You could do the product rule, or you could do distributive and then take the derivative of that. I'm going to go ahead and distribute. Okay, so now doing calculus, I'm going to take a first derivative, and I'm going to set that equal to 0 or undefined, but in this case it's going to be 0. I can take a 4 out, and so that would be 125 minus x. And it looks like I have a 0 at x equals 125. X equals 125 is a critical point, or is the x-coordinate of a critical point. And it looks like if I plug in a number smaller than 125, I would have a positive number. And if I plug in a number larger than 125, I would have a negative number. So I know that this 125, or the value at 125, would be a maximum. So that's what we wanted. We wanted the largest area. So now we can figure out we want to make sure we answer the question, what dimensions do we have? So we have a dimension of 125 for x. And then for y, we would have y equals 500 minus 2 times 125, which is 250. So y equals 250. So the dimensions are 125 by 250. All right, here's our next one. We have a rectangle that is sitting on the x-axis, and its upper two vertices are on this parabola, 9 minus x squared. I'm actually going to go to this, I'm going to look at this parabola a little bit more carefully so that you can understand the question better. I'm going to go to Desmos, and I have this graph here, and if I change this value, you can see that I could have a really skinny rectangle, I mean a really fat, wide rectangle, or it could be really narrow and tall. And so there are lots of infinitely many rectangles that I could have, but what I'm wondering is which one has the largest area. So that's what I'm trying to figure out. All right, so we're going to go back to what's our restriction. I'm drawing a rectangle in the XY plane, and I want to make it the largest area. The thing that's keeping me from just making it a million by a million comma a million is that my y coordinate has to be 9 minus x squared, because my parabola has to, I mean, my corner of my rectangle has to lie on that parabola. So that's my restriction, is the parabola. It's keeping me from making that rectangle cover the earth. Now what am I trying to optimize? I'm trying to find the largest area. So now I'm going to look at, if this ordered pair is x comma y, then that means that the height of the rectangle is y, and the width of the rectangle would actually be, this distance would be x, and then this distance would also be x, so the width would be 2x. So remember, we like to write the optimization equation as an f of x equation, just to remind ourselves that that's what we'll be doing calculus on. And the area of the rectangle would be 2x times y. Should bother you that you have an x and a y in an f of x equation, but it's okay because your restriction is going to get rid of the y. So we have 2x times 9 minus x squared. And now we're going to do calculus in order to optimize the area. So this is my f of x equation. I'm going to distribute. And take a derivative. And then we want to find the critical points. So we're going to look for where that's 0 or undefined. It's never undefined, so we're looking for where it's 0. And so we have x squared equals 3. So x is equal to plus or minus the square root of 3. But because of the way I drew this picture, my x comma y is in the first quadrant. So I'm just going to use x equals the square root of 3, because I decided when I drew my picture that x was going to be in the first quadrant. Now looking at f prime, so I can decide whether square root of 3 is a maximum or a minimum. If I put something smaller than the square root of 3 in, and because of the way I set this up, I'm going to go from 0 to 3, because then I'd be at the x-axis. If I put something smaller than the square root of 3 in, I do 3 minus that squared, so I would have a positive value. And if I put something larger than the square root of 3 in, I would have 3 minus that squared, and I'm subtracting more than I have, so this would be negative, and that means that my function is increasing up and then decreasing. So square root of 3 is the x-coordinate of a maximum, and that's what I want to know. Now my question is, what's the largest possible area? And since I have an equation for area right here, I can go ahead and just plug in square root of 3 into that equation to get the largest possible area. So I have 6 times 2. So 12 root 3 is the maximum area for this rectangle. Okay, we're going to do one last example. This is sum of two non-negative numbers is 20. What is the minimum sum of one number and the square of the other number? So the restriction is that the sum is 20. So x plus y has to be 20. And we are trying to find the minimum sum of one of the numbers and the square of the other number. I'm going to solve this for y. And I can decide that I would like to do x plus the square of y, or I could decide that I want to do y plus the square of x. And I'm just calling one number x as opposed to the other number. Either one of these two equations would be an okay equation to use. Because I'm squaring y and y is a whole function, I'd actually rather not use this one. I'd rather use this one because it's easier to look at. So I'm just going to have 20 minus x plus x squared for what I'm trying to optimize. Now I'm going to do calculus, and this is actually a time when we want to be really thoughtful as we do our calculus. So we're going to take the derivative of this. We have negative 1 plus 2x. So that would be 0 when x is equal to a half. But we actually have endpoints here. And remember, maximums and minimums can happen at endpoints. Non-negative means that the smallest that x could be would be 0, and the largest that x would be 20. So this is going to be a candidates test because we actually have endpoints here. So we're going to check the endpoints of 0 and 20 so that our numbers are non-negative. And then we're also going to check the critical value of 1/2. If I plug 0 into my function here, I get 20 minus 0 plus 0. If I plug 1/2 in, I get 20 minus a half plus a fourth. So that would be 20 minus a fourth. So that would be 19.75. And then if I plug in 20, I get 20 minus 20 plus 20 squared. So I get 400. This certainly looks like my maximum. And if I hadn't done calculus, I would have no idea about that x equals a half, giving me a minimum value of 19.75. So this is kind of a word of warning. You want to make sure that you're still thinking about endpoints. The reason we haven't had to worry about endpoints before, and I'm going to skip this problem and come back to it. The reason we haven't had to think about endpoints before is because this box would have an area of 0 at the endpoints. If x is equal to 3, we would no longer have a dimension. And on this one, if our x is equal to 0, again, we would no longer have a dimension. So we don't really have endpoints until we get to that third example. All right. Optimization is tough when you first get to it. You have a lot of manipulation that you have to do. Keep in mind you have 3 steps: restriction, optimize, calculus.